Welcome to the video for Graphical Behavior II, Day 5. In this video we're going to pull together everything we know about f, f prime, and f double prime to help us sketch a curve of the function. So this is a pretty comprehensive section because we pull together lots of algebra skills and calculus skills to draw a curve. The sort of thing our calculator can do for us very quickly, but we should be able to do by hand. Alright, so for this skill, since we are doing a lot of review and just pulling it together in one comprehensive aspect, what I'm going to do is a lot of it off camera, and I'll tell you what I'm going to do and then ask you to pause it, and you can do it, and then you can check it against the work I have. So our primary goal is to be able to look at a function and sketch what that function looks like. And so the way we're going to go about doing that is we're going to first find the first derivative and use that to determine where we're increasing and decreasing. We can also use that to identify where we have mins and maxes. And then we'll use our second derivative to find where we're concave up and concave down. And then we pull it all together into a sketch. So the first thing I'm going to do is use the first derivative to determine where the function is increasing and decreasing. So go ahead and pause this and take a shot at doing that on your own. Alright, so I took the first derivative and I factored it down, finding the critical values, figured out where it was increasing and decreasing, and I identified where a local min occurs. It occurs at x equals -2. If you plug -2 into the original function, you'll get where the y coordinate is, and that should be -29.6. Okay, and the local max is at 4,474.3333. So right away I could plot those 2 points and know that the curve passes through those. But before I get to that, let's go ahead and take a look at concavity. So I'm going to work on the concavity here, which means the second derivative, and you might want to pause it and try to tackle this on your own. Alright, so I took the second derivative, I factored it. I couldn't factor it further because this doesn't factor, so I used the quadratic formula to identify the possible inflection values, and I ran a number line chart with f prime prime and located where the points of inflection are. And so what we can do with this is then we can draw a graph based on all of the information that we have. So I'm going to start by drawing the horizontal axis, -1, -2, -3, -4, and 1, 2, 3, 4. And then the vertical axis I see goes very, very high, like up to 474 or 298. So I'm not going to really bother scaling the vertical axis. I'm just going to do relative scaling. And we'll plot these points. We start with a minimum at -2. We'll call this 29. Or -29.6. We have a point of inflection at roughly -1 and -16, so somewhere like there. We have another point of inflection at 0.5. Then we have one at 298, and a max occurs at 474. So somewhere up here. And this is a very poor job at scaling, but what we have is the function is concave up, and then it's concave down, concave up, and then concave down. And we have all of the information on the graph there, where the mins and maxes occur and where the points of inflection occur. With some more advanced algebra skills, we could possibly find what the x-intercepts are. Where does this cross, or where does this cross? Since this is a 5th degree polynomial, that's more or less out of the reach of the skill set that we have, so we'll leave it at that. I think if you succeeded at finding the mins and maxes and the points of inflection, you can successfully draw that it's decreasing to increasing to increasing to decreasing, or concave up, concave down, concave up, and concave down. So that's our target objective with these things, and I've given you, it looks like, 5 examples in the notes, and that's probably more than I want to cover in the video. So we'll do 1 or 2 of these more on the video, and then we'll hopefully try some of them out in class. So let's take a look at example B. Okay, so we'll start with the first derivative to determine increasing and decreasing behavior as well as the local max and min. So go ahead and pause the video and take a shot at that. So we took the derivative, we factored out the greatest power, and we found a critical value at 0 and at 8, and then we found the increasing and decreasing behavior. First derivative test tells us we have a maximum there and a minimum at 8. So there's the first derivative. Now let's take the second derivative to find our possible points of inflection. Alright, we took the second derivative. We factored out our highest power, which was x to the negative 1/3. Our lowest power, which was x to the negative 2/3. And then we found a critical possible inflection value at 0 and a possible inflection value at 1. Ran the test, calculated where our point of inflection was. And so we're going to use all of this to sketch a graph. We have a local max at 0, 0. We have a point of inflection at 1, negative 3. And we have a local min at 8, negative 16. 2, 3, 4, 5, 6, 7, 8. And down here, negative 16. And what we have is behavior that is increasing and concave down. And then we have the decreasing and then concave up. Alright, there's a rough sketch of what that graph looks like. I would strongly advise that after you get done drawing the sketch, you graph the equation in the calculator and see if you created something that looks vaguely familiar or similar to what you've drawn. Just keep in mind that your drawing may have a slightly different scaling on the axis than your calculator does. Okay, let's move on to part C. Alright, in part C, I'm going to leave finding the derivative and the second derivative to you, and all I'm going to do is write the number line charts and the conclusions that we have. But before we even get started, in pre-calculus, we should have learned how to sketch a rough drawing of this. We should have learned that there is a vertical asymptote at x equals 2, and there is also even a slant asymptote if we wanted to do the long division to find where that slant asymptote occurs. But we'll use calculus for solving this problem, and we'll start with the first derivative test. And I'm going to go and do both the first derivative test and the second derivative to find our maxes, mins, and points of inflection. So let's get to it. Go ahead and pause the video. Alright, so I used the quotient rule to find the first derivative, and then once I simplified my numerator and factored my numerator, I came down to having critical values at 0 and 4, and then there's also a location where the derivative doesn't exist. Technically this isn't a critical value because the function doesn't exist there, but we do want to include it in our number chart. And we find that it goes increasing, decreasing, then we have that vertical asymptote, and then decreasing to increasing. Our first derivative test tells us we have a local maximum at 0 and a local minimum at 4. So we locate those points, And then we move on to the second derivative. And the second derivative, we go through and do the quotient rule to this thing, and through a process of simplifying and factoring, we arrive at something that looks kind of like that for the second derivative. And we see the only possible inflection value occurs at 2. And again, remember, we have a vertical asymptote there, so there will not be a point of inflection there. When it comes to drawing the graph, we'll start by drawing the axes. We have a vertical asymptote at 2. If we wanted to, we could take the limit as x approaches 2 from the right and see that we have a positive infinity and a negative infinity if we wanted to do limit analysis. Then we can go through and plot these points. We have a local max at 0, negative 2. So a local max there, and we're concave down all on that side, so it probably does something like that. And then on the right side, we have a minimum at 4, 6. 6. 1, 2, 3, 4, 5, 6. There's our minimum, and we are all concave up on that side, so we probably come down and do something like that. If we went back and did the long division, we could actually find where exactly this slant asymptote is, but it adheres to that slant asymptote. But as I said, the important part is that you're able to find these things and then plot the specific points. If we're going to get into the art of drawing a perfect graph, then we would want to find that slant asymptote. Okay, for part D, I'm going to just give you the highlights, and I want you to be able to use the math to figure that out. So the highlights for part D, our first derivative, eventually we're trying to find the critical values, and we arrive at a point where we're like x squared plus 2 is equal to x squared, and that's never going to happen, basically, when is 2 equal to 0. And because of that, f prime does not have any critical values, so we can stick f prime of any number, and we find that the function is always greater than 0. So, or the derivative is always greater than 0. So it's basically a function that is always increasing. If we go to the second derivative, our second derivative, it takes a little bit of algebraic manipulation to get there, but we'll find that what we get is this as the second derivative, and that would tell us there's a possible inflection value at 0. So we drop 0 on our number line, and we see that it goes from concave up to concave down. So we do have a inflection point at 0, and it looks like that would occur at 0, 0. So we can write that in here, point of inflection at 0, 0. Drawing our graph, what we get is an inflection value at 0, 0, and it's increasing forever. So we have something that is going to look, there's increasing and concave up, and increasing and concave down. So we get a curve that looks like that, kind of like the cube root function, or maybe the arctan function, but not quite the cube root or the arctan. Alright, let's look at example E. Okay, with example E, our derivative is easier to do than definitely example D. We find that when we apply the chain rule, we get negative 2x e to the 4 minus x squared, and the only spot where this is equal to 0 is when x is 0. So our increasing and decreasing behavior is found thus, and we get it looks like a local maximum occurs at 0, comma e to the 4th. Let's write that in there. Max at 0, comma e to the 4th. Going to the second derivative will require us to use the product rule, and we get derivative of the first times the second plus the first times the derivative of the second. And with some creative rearranging, we can pull the e term to the front, and we can factor this as negative 2 plus 4x squared. And we see that there's going to be possible inflection values at positive and negative root 1/2. And we've got concave up, concave down, and concave up behavior. So when it comes to drawing the graph, we'll drop this in here. We have a max at 0, comma e to the negative 4th, no, positive 4th. Incidentally, this whole function will always be positive, so in theory you could say there's a horizontal asymptote at 0. And then we got our points of inflection occurs at these two locations, and we'll just kind of plop them. We'll call this negative 1/2, and it occurs somewhere here and here. If we actually plug that in, we can find out what the y coordinate was. I'll leave that to you. As far as concave up and down behavior, we're concave down in the middle and concave up on the ends. So it looks like we might have something kind of resembling the bell curve here. Alright, so there was our synopsis of combining everything we know about the first derivative and the second derivative to help us sketch a function. We can get really in depth with this and tackle these problems through extensive use of our algebra and calculus skills. But for the most part, I want you to be very comfortable with using f prime to determine increasing and decreasing behavior, as well as maxes and mins, and then using f double prime to determine your concavity as well as points of inflection. Thanks for watching. Have a good evening.